Hello everyone, in a new video on collinear algebra. So I took my own time yesterday to actually learn more outside of the video on learn more about binary relations, and I've arranged the summary here. So I'll just quickly do a recap by going through the summary instead of going through the whole video set of videos again. Anyway, so we came to know on the last video about Cartesian products uh, and what they are and stuff like that. So binary relation, um, so it's about relating one element from one set to another element on another set. So you have this basically a single connection between these two, and the connection is based on a given relation. Um, So binary relations are ordered pairs. So they are anti-symmetric. So what we mean by anti-symmetric, as we've introduced on the last videos, anti-symmetric is something you can't really interchange. So when you have a pair, you can't go A, comma B. You can go say A, comma B, but you can't go B, comma A. So this would basically change the meaning. And A, comma B means that there's a relation between A and B, so that the relation leads to B. Yeah. And binary, so it's only two elements in a pair. There are several ways to symbolize this, but the most and best formal way to formalize a relationship is by creating the set notation. But but generally, the symbol is just set A relation with B, where R is a relation of some sort. So you say A is R related to B, where A belongs to A to a set and B belongs to another set. An example of saying that in plain English: assume A is Bob and B is orange, and R is liking, so B likes an orange. Now note something, that this can happen on the same set, that we use two different sets here, the capital A set and the capital B set. And the elements are A of the capital A and B of the capital B. But anyways, the two sets are A and B. The binary relation can happen between the same sets. And that's what flexivity means anyway. So, and one thing to note is that the Cartesian product is the combination of all the elements in set A with the elements in set B. The binary relation is always a subset of the Cartesian product of sets involved, and it can also be empty, by the way. So binary relation can exist. Again, as I said, binary relation can exist on the same set. So and order is very, very, very important. When you go like Bob likes orange, you can't really go orange likes Bob. So the importance, the order is really important. The order of the group here is very, very important. And the example I've given here is that you say on the same set, instead of you going, so you say Bob is R related to Alice, and the relation of R is about the age, who's older. So you can go Bob is older than Alice, but you can't go Alice is older than Bob. It just won't make sense, right? Anyway, so and the elements in a set are always listed once, so there are no duplicated elements. You can't have like two Alices or two Bobs in the same set. Yeah. And sometimes when you do plot a graph, you might end up having the data points condensed or mostly located in a small area within the graph. Now, something to consider here is that you could expand that area and just by getting rid of the origin points and starting off from um, a number that really makes sense. And you can see here, this is what scatter graph is all about, and scatter plot. And you can see here in the graphs, you can see that it's starting from 0 to 100, which is which are the numbers that really expand on the data we have and really brings them out. And then when you have the data plotted, you can draw a line, and usually the most common algorithm to draw this line is called the square distance, the square difference, I think. So basically you calculate r square from each point, and then you get the average, and then you just draw on that. Usually it's just a predefined algorithm that you could simply use to get the correlation between the data. So when you have an uptrend, you have a positive correlation, negative trend, negative correlation. This basically means that in this case you have the height and weight. So the more heavier you are, the more heavier the weight, the shorter you are, or the shorter the object. Anyways, so if these data points are close to the correlation line, then you say there is a strong correlation, or do you say there is a weak correlation? In this case, in this drawing here, there is no correlation whatsoever, so you can just simply say it's uncorrelated. This correlation line is also called the line of best fit. And you can think of this, there's one example that is mentioned in the video, in which there is this constructor who tries to build a road between several towns that goes through several towns, and the best way to do it is to build the road closest to all of the towns. And this is where so you could imagine that these data points are actually the towns, and you could build a line a road that really brings all this together, closest to each and every one of them, the average, I mean, closest to all buildings combined. Anyways, so as I said, the least squares is basically calculating the vertical distances to the line. So you build from the top, you go down vertically, and then you go vertically from here, and then you get the average distances among all of these data lines. Alright, so that's that, and then you move on. So that's the binary relation, and let's really quickly take a look at what would be the as to the topic. Mappings we've done, so there is the ordering and equivalence relations. So we've done the equivalence relation, and so we know that anisymmetric is a property of a pair of a binary relation, right? Of an ordered binary relation. I think so if R is a subset of the Cartesian product, so you're given two sets. A subset of the Cartesian product is said to be a relation between S and T. Okay, so if R is a subset of the Cartesian product and x and y belongs to the set of real numbers, then it is common to write x is R related to y to show that x and y are R related. In particular, consider the relations symbolized by less than or equal and defined as the following on S. Okay. Yeah, so ordering is very important. And the relation on a non-empty set as having these three properties is said to be partial ordering, and S is said to be partially ordered sets. We will be writing, okay, so there is this x is less than or equal y, and y is less than or equal x, so antisymmetric non-symmetric. So there is non-symmetric and there is anti-symmetric. So there is this question here: is an anti-symmetric and asymmetric relation the same? Are irreflexive and reflexive the same? I don't understand the difference between an anti-symmetric and asymmetric relation. From my understanding, if there is not any element where, okay. But what if you have only one, not all double arrows? Okay, a binary relation. So you have symmetric, asymmetric, and anti-symmetric. Binary relation in a, so this is symmetric, married to. A binary relation R on a set X is asymmetric when is a father of, so that's asymmetric. Anti-symmetric if there is no pair of distinct elements of X, each of which is related by R to the other. There is no pair of distinct elements of X. The usual order relation, less than or upon the real numbers. Every asymmetric relation is also anti-symmetric relation. Your proposal for a symmetric is if there is not any element where xy then yx, it sounds like moving inwards is equivalent to. This guy used several notations, which is interesting. Every asymmetric relation is also antisymmetric, but if antisymmetric relation contains pair of the form AA, then it cannot be asymmetric. Antisymmetric means that only one way for both, that the only one way for both A related are related B and B are related A to hold is if A equals B. It can be reflexive, so this is what antisymmetric mean. Asymmetric is the same except that it can't be reflexive. Never has both A and B. Asymmetric. Hit them, they will hit you back. If you hit them, they will ignore you. So it's actually let me check the videos as well. Let's see when do they talk about this subject. Before doing that, I'll just write one quick note that I forgot to write, which is to evaluate row function. The next subject in here is yesterday I've actually studied real valued functions of real variable. Real variable is basically you have a set of real numbers. Scatter plots, vertical line test, we already know this. that if a function is actually a function or not a function. When you have then you have multivariable functions, in which you can go, if it's 3 elements, you could go you could go a 3D plane. So next up is the equation, linear equations, slope, point slope, tool form, standard form, linear equation in the real world, solving literal equations. So I don't think we are introduced to what is called partial ordering here. So let's try to get to grasp the difference between asymmetric and antisymmetric, and what does it really mean. Okay, so we know that symmetric, you could go A or B and B or A, so that's basically a property of the what is it being? A property of what is called equivalence relation. So symmetric is not really a problem. The problem is in asymmetric and antisymmetric. So asymmetric is father of. Okay, so antisymmetric. Let's look at this. Maybe this has a better explanation. Asymmetric is stronger than simply not symmetric. But as I try to perceive this statement, both appear to be the same to me. Example, parent of is asymmetric property. If A is a parent of B, B cannot be a parent of A. We are of the same conclusion if we call this property to be not symmetric. Just saying I don't agree. This terminology is clear. It's too natural to interchange A and not to have distinct meaning for them. I don't know. Stronger would imply that asymmetric would imply not symmetric, which of course not true for empty relation based on the answers below. Never found this terminology. In fact, in my mind, asymmetric simply means that it lacks the property of symmetry. So the relation may have some symmetric pairs and others that aren't. It is also due to the etymology of the word, which actually means this. So if a property is symmetric, then there is a two-way arrow. If someone is a blood relative of me, then I have to be a blood relative of them. If a property is not symmetric, then there can be one arrow or two. If I like someone, then they may or may not like me. Either case could be true. If a property is asymmetric, then having one arrow means that there is definitely cannot be two. Okay, if someone is my parent, they cannot be their parent. So basically the difference between non-symmetric and asymmetric is that in one we might have two arrows some of the time, but in the other way we can never have the second arrow. So asymmetric is stronger. No, it's not, but they are related. Antisymmetric is when there are no two distinct objects with two arrows. So two arrows implies that the objects are the same. Asymmetric is an example of antisymmetry, but it does not cover every possibility, so they are distinct relations. Okay. So what did it say here? What did they say in the book? It said antisymmetry. Antisymmetry yeah, so some are actually. This is a really nice explanation. Then this guy really nailed, hit the hammer home, hit the nail home. There we go. So basically, there's that. Alright, so the next topic of discussion would be, I think that covers it pretty good. So partial ordering is when you have antisymmetric. Asymmetric is total ordering. Right, so I'm not sure how important this is, but just skip through it. Not sure if I'm not really sure why the book is cardinality and the real number system. Yeah. Open interval, closed, we've covered those. Absolute value, induction. I'm sure the induction is all about though. And factorial. Oh yeah, we've actually studied this. We've actually went through this, I believe. Yeah. Complex numbers. Yeah, well, apparently from what is being reflected here, I mean, this is the formula to, what is it? Now this is the formula to get the number of, yeah. Okay. Then you went through geometry. So these are all very important here. Additional properties of the integers. I'm starting to doubt the book. Well, I understand it covers most of the subjects, but come on. We've got some weird stuff going on here. Well, this shouldn't stop us, right? We could just keep going. Alright, so let's hold this for now. Let's go back here. Linear equations. Should we start with linear equations then? Yeah, let's do that.
And welcome to YU. We have seen that many functions encountered in mathematics are real-valued functions of a real variable. These functions take their input values from a real variable called the independent variable, and for each valid input value produce one specific real output value. When x is used as the input variable, the output value is typically assigned to the variable y, called the dependent variable. These values of x and y can be visually represented on the Cartesian plane. This visual representation is called the graph of the function, and the process of creating it is called graphing the function. Real-valued functions of a real variable are typically described by an equation. For example, the equation which describes the function represented by this graph is y equals 2x. This function is said to be linear, since its graph is a line in the Cartesian plane. Linear functions are very simple, but extremely important in mathematics. This is not only because many natural phenomena can be modeled by linear equations, but also because more complicated functions often appear linear when viewed on a small enough scale. Notice that as we examine smaller and smaller regions of this curve, the graph looks more and more linear. The fact that many functions appear linear on a small scale is the logical basis of branches of mathematics such as calculus. It is this same principle which allows us to treat the Earth as a flat plane locally, even though on a large scale its surface is actually curved. Lines are simple geometric shapes, and so the equations which describe them are also simple. As an example, let's create an equation which describes this linear graph. Notice that the x and y coordinates of each point on this line have the same value. For instance, when x has a value of 5, y also has a value of 5. This equality between x and y applies to every point on this line. Therefore, the equation y equals x describes this function. This equation states the condition that the x and y coordinates of every point on the graph have the same value. We say that the coordinates of any point on this line satisfy this equation. We can verify this by replacing the variables x and y in the equation by the coordinates of any individual point. If this creates a true statement, then the coordinates satisfy the equation and the point lies on the graph. For instance, the coordinates 3, 3 satisfy this equation, since replacing both x and y by 3 creates the true statement 3 equals 3. Therefore, the point whose coordinates are 3, 3 lies on this line. On the other hand, we can confirm that the point 4, 3 does not lie on this line, since substituting these coordinates into the equation creates a false statement. Now, instead of the equation y equals x, let's see what graph is created by the equation y equals 2x. In this equation, the variable x is multiplied by the constant 2. A constant multiplier of a variable is called the coefficient of the variable. In this equation, 2 is the coefficient of the variable x. This equation states that the y-coordinate of each point in the graph has a value twice that of the x-coordinate. For example, if the x-coordinate of a point is 3, then the y-coordinate of that point must be 6. Or if x is 2, then y will be 4. If we continue to calculate more points for this equation, we will see that these points all fall on a line running through the origin. We can confirm that this line passes through the origin, since substituting the coordinates 0, 0 into this equation results in a true statement. Therefore, the point 0, 0 lies on this line. Let's see what happens if we make the x coefficient even larger, say 3. We can see that if x equals 2, y will equal 3 times that value, or 6. So the point 2, 6 lies on this graph. Calculating y for several more values of x, we see that once again the collection of all the points which satisfy this equation form a line passing through the origin. The graphs of all the equations which we have seen are lines which pass through the origin and slope upwards as we move towards the right. The only difference between these equations is the coefficient of x. Notice that the larger the x coefficient, the greater the slope of the line. But what if the x coefficient is negative? For example, let's say we pick an x coefficient of -1. Now if x is equal to 3, y must be -3. Likewise, if x is negative 3, then y will be positive 3. This equation also describes a line which passes through the origin, but slopes in the opposite direction from the lines formed by equations with positive coefficients. This line slopes downwards as we move to the right. Increasing the magnitude of this negative coefficient produces lines with a greater downward slope. So the sign of the multiplier determines whether the line slopes up or down, and the magnitude of the multiplier determines the magnitude of the slope.
Should write this down.
Lines which slope up as we move to the right are said to have a positive slope, and lines which slope down are said to have a negative slope. So what happens if we make the x coefficient 0? Since 0 times x is always 0 regardless of the value of x, this equation can be written as y equals 0. This equation states that regardless of the value of the x-coordinate, every point's y-coordinate will be 0. So this equation describes a horizontal line running through the origin. This fits the relationship we have seen between the x-coefficient and the slope, since an x-coefficient of 0 produces a graph with 0 slope. So for linear functions, the coefficient of the independent variable x determines the slope of the graph. The coefficient's sign determines the sign of the slope, and the coefficient's magnitude determines the magnitude of the slope. The smaller the magnitude of the x-coefficient, the smaller the slope. And when the x-coefficient is 0, the slope will be 0, and the graph is a horizontal line. But is it possible for an equation to describe a vertical line? We have seen that as the x-coefficient gets larger, the slope of the graph becomes closer to vertical. However, no matter how large the coefficient becomes, the line will never be exactly vertical. It would require an infinitely large x-coefficient to produce a vertical line. But infinity is not a number, and therefore cannot be used as a coefficient. However, a vertical line can be described by the equation x equals 0. But this equation does not describe a function of x, since it associates multiple values of y with a single x value. So with an equation of the form y equals mx, where m is some constant, we can describe any non-vertical line passing through the origin. By choosing the value of m, we can create a line with any slope we please. In the next lecture, we will see how to create functions whose graphs are lines which do not pass through the origin.
Alright, so that will be the next lecture. But I need to figure out, before moving on to the next topic, I need to figure out this stuff. Apparently this is important given it's mentioned in the initial version. I mean in the review chapter here. Now I'm not really sure how this should be explained. I understand this is just a summary, that's why there are several confusing points and confusing aspects in here. But I guess I'll just have to look for a source that really fully explains this. We've covered most of the important topics like the ordered pairs and the ordered list, the Cartesian product of a set, and then the multivariate functions, and also hopefully they would make covering these topics a lot easier for us. So I'll look into this before we jump into. I mean, the subject is this series of videos are quite comprehensive in the sense that they get you up to speed really quickly, but the book apparently has several concepts and terminologies that aren't covered anywhere, so we should consider these. Alright, so until the next video, have a good one. Oh yeah, before I end this video, I think we should call this video, we should title it Binary Relations and Linear Equations.